Last lecture we were studying isomorphism of groups. We will do one more example of isomorphism. The first group G that we consider will be the symmetries of the equilateral triangle. So, consider the equilateral triangle in a plane. Let's just name the vertices as A, B and C. The symmetries of these would be, there will be 6 symmetries, 3 corresponding to rotation and 3 corresponding to reflection about a vertex. Okay, so let us name these elements. So, first is the identity permutation, or which does not do anything, and the second would be the rotation by 120 degree about the center. Okay, so, suppose you look at the centroid of the equilateral triangle and you consider rotation by 120 degree, you will get one particular element of this group. So, let us call that as R. Okay, so, that is rotation by 120 degree, and then there is a rotation by 240 degree. So, R would send vertex. So, if you look at R, this is the permutation that sends A to the position of C and C to B. If you rotate once more, let us denote that by S, then we would get okay. So, and then so these are the 3 corresponding to rotation, and then you can reflect about any one of the axes. Okay, so, if you reflect about the vertex about the axis joining A to the centroid, B and C flips. Okay, so, let us call that as X. So, that is this permutation which keeps A wherever it is and then flips B and C. So, C comes here and B comes here. So, this is the operation flipping about this particular axis that we will call by X, and then there are 2 more other axes. If you flip about B, that we will call as Y, and if we flip about, let us say, the vertex C, what we get is the element Z or Z. Okay, so, our group G will basically consist of these 6 elements I, R, S, X, Y and Z. Okay. So, these elements, when they multiply, this is the dihedral group, they multiply in a certain way, and you can verify that they do form a group under the operation of compositions of these operations. Okay. For example, if you combine R with X, okay, so R basically rotates. If you start with A, B, C as labels, so when you say R times X, it means you are first applying X. So, when you apply X, B and C gets flipped. So, you will end up in the configuration A, C, B, and then you are rotating. So, you will reach A, B and C. Okay. Now, this is same as flipping about B. If you have taken the vertex B and if you have flipped about that, what you get is this. So, R x is going to be equal to Y. Okay. So, you can do all the other operations and verify that these do indeed form a group. So, this is our first group. The second group that we consider, which we will denote by H, will consist of matrices. Okay. So, these are matrices, special kind of matrices, where the first element, the elements are essentially coming from Z3. Okay. So, H basically consists of matrices whose elements are members of Z3. Okay. By Z3 we mean numbers from 0 to 2. Okay. So, alpha and beta here are going to be members of Z3 and the other two elements are fixed 0 and 1, and we have this restriction that alpha is not equal to 0. In particular, if you think of these matrices and if you look at their determinant, that is going to be non-zero because the determinant is going to be alpha. So, H consists of all elements of the form alpha, beta, 0, 1, where alpha is not equal to 0 and alpha, beta are elements of Z3. Okay. So, now we have specified the matrices, and if you look at all these matrices, what is the matrix multiplication or the operation that we are interested in here? What is the operation that makes these elements a group? So, we will consider the usual matrix multiplication, but carried out mod 3. Okay. For example, if you take the matrix 2, 2, 0, 1, this is one of the elements of H because 2 and 2 belongs to Z3 and 2 is not equal to 0. This times, let us say the same element 2, 2, 0, 1, this will be equal to, you can do the usual matrix multiplication and then you would have got 2 into 2 is 4. Okay. But this is not an element of, so this is the usual matrix multiplication. But we will do the matrix multiplication mod 3. So, then we will get the product as 1, 0, 0, 1. Okay. So, in particular, if you are doing alpha 1, beta 1, 0, 1 times alpha 2, beta 2, 0, 1, what we will get is and these mod 3 is our final answer. Okay. So, clearly this multiplication is a well defined operation, and you can verify that if you took alpha 1 and alpha 2 as not equal to 0, then when you multiply them out you will still get a non-zero element mod 3. Okay. So, this is our second set H. So, H has how many elements? Okay. H also will have 6 elements because alpha, there are 2 choices for alpha, namely 1 and 2, and beta has 3 choices 0, 1 and 2. Okay. So, the total number of choices is 2 times 3, that is 6. So, we can write these 6 elements as, when alpha is 1, we have 1, 0, 0, 1, 1, 1, 0, 1, 1, 2, 0, 1. And then 2, 0, 0, 1, 2, 1, 0, 1 and 2, 2, 0, 1. So, these are 6 elements, and now we have, and these form a, you can check that under the operation that we have defined, these 6 elements do form a group. So, now we have 2 groups G and H, which both contains 6 elements. So, it is easy to get a bijection between them, but can we get a bijection which is going to be an isomorphism between the 2 groups? I will give the isomorphism, you can check it, that the function that I give, the bijection that I give is indeed an isomorphism. So, 0 maps to, let us say, capital I, and this is capital R, this is capital S, this if you call as X, Y and Z. Check that mapping the small letters to the capital letters indeed is an isomorphism. Okay. So, in order to check that the two groups G1 and G2 are isomorphic, or G and H are isomorphic, we need to check two things. The first condition is there exists a bijection, say f from G to H, and second, for this function f of G1 G2, that is, if you combine G1 and G2, you get another element of G. This combination is done as per the operation inside G, and if you combine them and look at its image under f, that is going to be same as if you had looked at the images of G1 and G2 and then combined it under the operation in H. So, whatever is that result, if these two results are same, then we say that G and H are isomorphic. So, if only one of these conditions is satisfied, namely the second condition, then we will call this function f, which has this property, as a homomorphism. That means we are unable to find a bijection, but there is some function which satisfies condition 2, then we will say that this is a homomorphism. So, homomorphism is same as only condition 2 is satisfied. Okay. So, we will study about homomorphism in more detail in the coming lectures. So, now that we have understood what is isomorphism, in the earlier examples, maybe it was straightforward to see that the sets that we considered were isomorphic. Here the groups involved are simple groups, they are just 6 elements. So, one can actually try out, but it is not obvious to the simple eye that these groups are indeed isomorphic under this particular mapping. We will learn some more terms from group theory mentioned about this particular term, cyclic groups. So, the definition of cyclic group says that all elements can be written as powers of some element. Okay. So, G is cyclic if there exists small g element of G such that the set G is equal to say G power 0, G power plus minus 1, G power plus minus 2, and so on. Okay. So, when we write G power minus 1, that would mean the inverse of G power 1, and G power minus I is G power I inverse. Okay. We could also think of this as same as G power I, G power minus 1 multiplied with itself I times. Okay. When it is a group, all these properties must be true. So, a cyclic group is a group where every element can be written in the form of G power I for some integer I could be in particular 0. Okay. In case of, so this is the general cyclic group. In case of finite group, this condition would amount to G being equal to, let us say, G power 1, G power 2, and so on up to G power n for some particular n. Okay. Or here n will be the order of the group and it will be the order of the element. Okay. So, finite group means every element can be generated by just multiplying one element with itself enough number of times. So, in particular, if you looked at the roots of unity, in the complex roots of unity, that is going to be a finite cyclic group of order n. And if you are looking at the nth root, then you will get the a finite group of order n. You can verify that up to isomorphism, there is only one finite cyclic group, or one do not require the condition of finiteness. Up to isomorphism, there is only one cyclic group of any order. Okay. The next concept that we will learn is that of direct product of groups. Okay. So, consider a group A and consider a group B. Okay. We can take the direct product of these two groups. We will write it as A multiply A direct product B. Okay. So, this consists of say all pairs of the form AB such that A belongs to capital A and B belongs to capital B. If you take these collection of elements, what operation makes them a group? We could multiply the elements coordinate wise and do the operation in the corresponding group. For example, if we had taken, let us say, the group, let us say Z6, this will consist of elements 0, 1 up to 5, and let us say we consider Z6 star, which will consist of all elements which are relatively prime to 6, namely 1, 2 is gone, 3, 4. Okay. So, Z6 direct product Z6 under multiplication, that is going to be consisting of 12 elements, namely 0, 1, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1 and 0, 5, 1, 5, 2, 5, 3, 5, 4, 5 and 5, 5. So, these are the 6 elements, and if you want to multiply 2 elements, let us say if you want to multiply 4, 5 with 1, 5. Okay. So, 1 comma 5 multiplied by 4 comma 5, that is going to be equal to 1 combined with 4. So, 1 and 4 are combined in Z6. So, 1 plus 4, that is going to give you 5. If you had taken, let us say, instead of 1 5, if you had taken 3 5 and 4 5, 3 and 4 will combine to give 7. The operation was addition, but we have to do it mod 6 and therefore, we will get 1, and 5 and 5 will combine to give, 5 times 5 is 25, but mod 6, that is going to be 1. Okay. So, that gives you identity, not identity, that gives 1 comma 1. Okay. The identity of this particular group will in fact be 0 comma 1. Okay. So, this is defined as the direct product of groups. Okay. Let us look at some simple direct products. If you take, let us say, C2, okay, by C2 we mean the cyclic group of order n of 2 elements. Okay, we can write this as 1 comma x and let us say C3, which is a cyclic group of order 3, and we can refer to the elements as 1, y and y square. Okay. Now, if you take the direct product of these two, what we will get is a set consisting of 1 1, 1 y square, x1, xy, xy square. These are the 6 elements, and you can check that if you look at elements xy and its powers. So, xy's powers, let us write it down, that is going to be xy multiplied with xy. So, you will get x square y square as a first element, x cube y cube, x raised to 4 y raised to 4, x raised to 5 y raised to 5, x raised to 6 y raised to 6 and so on. Okay. There might be other elements, but if you look at x raised to 6, that is going to be identity, because x square is identity, and y raised to 6 is going to be identity, because y cube is identity. Okay. So, that is, so we do not have to continue further ahead, but are we sure that these 5 elements are all distinct? Now, xy is same as xy, that is one element that is present. X square is going to be identity, so this is going to be 1 y square, and x cube is just x 1 and x raised to 4 y raised to 4 is 1 y, because y cube was 1, and this is x comma y square. Okay. So, note that this collection, okay, instead of E we will write it as 1 1. This is a group with 6 elements, 6 distinct elements, and therefore, if you look at x y and look at the set generated by x y, okay, that means considering all the powers of x y, we get the complete collection, and therefore, C 2 times C 3, the direct product is isomorphic to the cyclic group with 6 elements. So, we can wonder whether this is a general rule, that means if you take the group of order I and order j, the cyclic group of these orders, and then multiply, do you get the cyclic group of order I times j? That is not always the case, we will see by an example, and you can try to answer the question as to when will these groups be isomorphic, that is when will Ci times Cj be isomorphic to Ci times j. Okay. When will this, what is a necessary and sufficient condition for such a thing happening? Now, first we will see why this is not always the case, because if you take C2 and C4, okay, and we can ask this question, is it isomorphic to C8? You can immediately see that that is not going to be the case, because the cyclic group of order 8 will have an element of order 8. There is going to be one element which generates the entire thing, whereas if you take any element in C2 times C4, okay, so let us call that as alpha comma beta. Okay. Now, if you raise it to the 4th power, alpha beta power 4, what you will get is alpha raised to 4 beta raised to 4. Now, alpha is from C2, so alpha raised to 4 is going to be the identity of C2, and beta raised to 4, that is from a group of size 4, and that is going to be equal to identity. Okay. Any element, you can check that any element in C4, if you multiply with itself or perform the group operation 4 times, then you are going to get identity, and therefore, there is not going to be any element of order 8, and therefore, these are going to be different. Okay. The next concept that we will see is that of subgroups. So, one thing that we did not explicitly mention was, if we define the direct product of groups in this particular manner, why is it that it will always be a group? So, this is a question that you can bother, is A direct product B always a group? Okay. We have to check 4 conditions. First is the group operation well defined. Okay. Clearly it is, because you take 2 elements, let us say alpha 1 beta 1 and multiply it with alpha 2 beta 2. Alpha 1 and alpha 2 can be combined in A, beta 1 and beta 2 can be combined in B, and the resultant element is clearly an element of the set that we have described. And since now the operation is well defined, we can check if it is associative. It is also yes, because that follows from the associativity of A and B. Because the underlying groups A and B are associative, you can verify that it translates into associativity of A times B, A direct product B. The third is the identity property. Okay. So, let us say EA is the identity of A and EB is the identity of B. This will act as the identity of A direct product B. This is easy to check for the conditions of identity. A, EB multiplied with any element AB. This is going to be EA combined with A and EB combined with B. By the property of EA being the identity of A, this will give you A, and EB times B similarly will give you B. Okay, so that can be easily verified, and similarly you can verify inverse as well. Okay, if you have an element AB, its inverse is going to be A inverse B inverse. So, A inverse B inverse is the inverse of A comma B. Okay. So, direct product will always be a group, and lot of properties from the group would translate into properties of the direct product. For example, if you take abelian groups A and B, their product will also remain abelian. Okay. That is, commutativity is preserved under this, but that is not true for all properties. If A and B are cyclic, that does not necessarily mean that A times B is going to be cyclic. Okay. The next concept that we will learn is that of subgroups. Okay, the notion is very simple. So, if you have a group G, when we say G is a group, we mean that G is the name of the set and there is an operation defined on that which makes it a group. Okay. So, if H is a subset of G and H is a group with the operation now being restricted. Okay, so, we do not take these elements and look at a completely different operation, but we look at the same operation on G, but restricted to the elements of H. So, under that, if H is a group, then H is subgroup. This is the definition of a subgroup. Okay. So, for example, if you consider say 0, 1, 2, 3, 4, 5. Okay, this is C6, the cyclic group of order 6, and or we can also think of this as Z6, it is the additive group. Okay. This is a group. Now, if you look at, let us say, elements 1 and 5 under mod 6 multiplication, if you took 1 5, that is a subset of the group that you have considered, but the operation that you are considering is changed. So, this will not be called as a subgroup of set 6, whereas if you take elements 0, 2 and 4, this is a subgroup of Z6. Okay, you are considering just the even elements of Z6. And under the same operation, that is mod 6 addition, if you look at these elements, they form a subgroup with 0 acting as the identity, and 2's inverse would be 4 and 4's inverse would be 2. Okay. So, now let us consider an arbitrary group G and let us define what is Z of G. Okay. So, this is defined as all the elements belonging to G such that Zg is equal to Gz for all G belonging to G. Okay. So, we are given a group, let us call that as G, and we are picking those elements such that they commute with every other element. If you take this collection, we will call this collection by a name. This is called as the center of G. Now, first question would be, is this non-empty collection? Clearly, identity is one element which has this property, identity times G is equal to G times identity. Okay. So, this is a non-empty collection, and if you have, let us say, two elements Z1 and Z2 which belongs to Zg, what about Z1 times Z2? Okay, so let us look at Z1, Z2 times any element. This is equal to, by associativity you can write it as Z1, Z2G, and Z2G, because Z2 was an element in the center, this is equal to Z1 G Z2. And now again we can apply associativity and write it as Z1 G times Z2, and that is by Z1 being an element of the center, this is equal to G Z1 times Z2. Okay. So, Z1 Z2 G is equal to G Z1 Z2 for any element G. So, whatever we did here was true for all G, and therefore, if you have two elements, their product is also going to belong to Zg. So, if you have some elements, this set has the property that it is closed under that operation. Okay. Zg is a collection, it is a non-empty collection, and now you take any two elements in Zg and you can combine them, and the resultant element is still going to be an element. So, this is one property that Zg has. So, we can write this as Zg is closed under multiplication. So, let us ask another question, what about Z inverse? Okay. So, Z belongs to G, does Z inverse also belong to G? Okay. Now, if this would mean Z inverse small g is equal to G Z inverse, this is what we need to prove. That is almost the same statement as the corresponding statement for Z. So, Zg is equal to Gz. So, if you just multiply, so consider this equation and multiply with Z inverse on both left and right. So, both sides if you multiply with Z inverse, what you get is Z inverse Zg Z inverse is equal to Z inverse G Z Z inverse. Now, these combine to give identity and this also combine to give identity, and therefore, you get G Z inverse is equal to Z inverse G, and that is what we wanted at the start, and that is same as this equation. So, Zg has this additional property that this is closed under taking inverses. Okay. So, you have a collection which is a property that you take two elements, combine them by the operation of the group, still the element is going to be there inside this collection, and you take any element, its inverse is also present. Okay. Now, any collection which is these two properties, so will in fact be a group. Okay. So, that is if you take G, so take a group G, consider any subset of G which is closed under inverses and is closed under multiplication. So, multiplication here means the group operation. Okay. So, let us call the subset as H, then H will be a subgroup of G. Okay. So, that is a theorem, we will prove that, but if we assume this theorem, we now automatically know that Zg will in fact be a group for any G, finite or infinite, does not matter. Take arbitrary group, take any arbitrary group, and if you can find a sub collection of this which is closed under these two operations, then that will be a subgroup. Okay. In particular, you could take the entire group, and trivially these two properties are true, and trivially the entire group is a subgroup of itself. Okay. There are two trivial subgroups of a group, namely the full group and the group consisting of only the identity element is also a subgroup. Clearly, the statement is true for both these cases, it is true for all the other cases as well. We will see that in a while. Okay. So, how do we show that H is a subgroup? First of all, if you take H, this operation is going to be well defined. So, let us say star is the operation Okay. Now, star is well defined on H itself because H is closed under the multiplication operation. Okay. And clearly, as star was associative, it will still remain associative. So, star remains associative on H. And will identity be present inside this? Okay. So, look at any element. So, this so take any group, take any subset. So, here we mean a non-empty subset. Okay. So, since it is non-empty, there is at least one particular element A, and clearly because it is closed under inverses. So, A belongs to H, therefore, A inverse also belongs to H because it is closed under inverses. Now, since A inverse is there, A star A inverse also belongs to H, therefore, identity belongs to H. Okay. So, we have a collection which contains identity, it is associative, the operation is well defined. The only additional property that we need to verify is that every element has an inverse, but that is something that we have already taken care of in one of our assumptions, and therefore, H will be a subgroup of G. Now, this inverse condition is a special condition that is required only when the group is an infinite group. If it is not infinite, suppose you look at a finite group, then the only condition that you have to check is that the subset is closed under multiplication. Okay, why is that so? If you look at any collection, so suppose G is finite, then second condition suffices. Okay, why is that so? Take any element. Okay, if H contained only the identity element, then clearly it is a subgroup. So, if there was a non-identity element present inside it, then call it as A. If you look at A square, so on. Okay. At some point, A to the power k has to appear such that this is equal to identity. Okay. Because otherwise, this is going to be an infinite collection. So, we can just simply argue that since when we are considering A square and so on, some point of time there should be a repetition, and let us say that the first repetition is at I and j, ai is equal to aj. But if this was the case, if we look at the inverses of A in the original group, let us call that as A raised to minus I. So, inverse of A raised to I is A raised to minus I, that when multiplied we will get A raised to j minus I is equal to identity. Okay. So, clearly if you consider one element and its powers, at some point of time identity is surely going to appear. Okay. So, we can assume that if you consider A square, so for some A raised to k you are going to get this as identity, and therefore, the inverse of A is A raised to k minus 1. Okay. Because A raised to k minus 1 multiplied by A is A raised to k, that is going to be equal to identity. Since this is true for any element A, will definitely have an inverse when when G is a finite group. Okay. We will stop here and continue our study of group theory in the next lecture.